and me. So I will take 3 classes, whereas Professor Kaushal will take 1 class. He'll be taking tomorrow's class, Thursday's class, whereas I will take today's class, Wednesday, and also on the Friday's class, which is a double lecture starting at 9 in the morning. So what this course is all about. The course is essentially the genesis of this course was, I mean, conceptually, it was initially created by 2 professors of University of Wisconsin at Madison, Bird and Lightfoot. So it was Professor Bird who first thought that why not teach chemical engineering in a different way. It's a paradigm shift of teaching in fluid mechanics. Instead of concentrating on fluid mechanics, heat transfer, and mass transfer, it could also be taught as an unified treatment of transport process where the amount transferred is proportional to a gradient. For example, the amount of heat transfer which you have studied is proportional to the temperature gradient for the case of conductive heat flow. The amount of species transfer is principally dependent upon the concentration gradient. The amount of momentum transfer is proportional to the velocity gradient. And the proportionality constant of all these relations are thermophysical properties, unique properties of the system, namely viscosity for momentum transfer, thermal conductivity, and the diffusion coefficient. So if you think about Newton's law of viscosity, Fourier's law of conduction, and Fick's law of diffusion, all these 3 laws connect the flux with the gradient of something that you can measure, for example, velocity, concentration, and or temperature. So this is the basis for the unified treatment of transport phenomena, which was initiated by Professor Bird at Wisconsin, and Professor Lightfoot was Professor Bird's colleague or student, I do not recall. So these 3 faculty members, they have in 1960s and 70s, they published a book called Transport Phenomena by Bird, Stewart, Lightfoot, which still today is probably one of the best treatments of the unified treatment of chemical engineering processes. So here we are going to follow them and try to see what new has been added from their time, which would help us in getting a more fundamental insight into the chemical engineering processes. So of course, the first book is going to be Transport Phenomena by Bird, Stewart, and Lightfoot. We are also going to, I have also included a few of the recent books which have come up in this. The number 4 and 5 are well known to you. 2 and 3, Transport Phenomena by Plowski, and Heat and Mass Transfer, a transport phenomena approaching, is by Professor K.S. Gandhi of IISc Bangalore, one of the most well-known chemical engineering faculty of our time. So Professor Gandhi's book is also going to be relevant in here, but the textbook will remain Bird, Stewart, Lightfoot. And I think you have studied heat transfer using the Incroperes book, is it not?
Yes, sir.
Okay, so that was the textbook. So these 2 textbooks are quite well known to you. And with this, then I can go to the what's going to be the grading criteria, and I'm going to talk about my part only. Professor Kaushal will have his own way of grading. So in my case, it's going to be 3 tests of 1 hour duration. The tests are going to be performed on Moodle, and it would be a combination of short questions and slightly longer, more involved type of problems. All the class material will be uploaded in Moodle. So you will have, if you have the Moodle, I mean, you must have Moodle account. So the class notes, etc., the assignments, the solutions, would be there on module. So the what am I going to cover in my part of the course? Something like formulation and solution of momentum transfer, Navier-Stokes equation. These two are already known to you. So I would be able to quickly go through this, and I will just do a quick recap of Navier-Stokes equation so as to bring you back to wherever you were at the end of your first semester in your second year. But the applications of Navier-Stokes equation that we are going to concentrate on in in this course are going to be slightly different from what we have done in fluid mechanics. So the first class or first one or two classes will be problems similar to what we have done. In fact, the same problems, I'll go through it very quickly, and then we are going to go into take a different approach and try to solve problems in which you have to use logic, you have to use order of magnitude analysis to simplify the Navier-Stokes equation and bring it to a form which can probably be solved analytically. So this order of magnitude idea and how that can be used to simplify Navier-Stokes equation would be the new thing which we would learn in this part of the course. Then comes the boundary layer concepts. I have introduced boundary layers to some extent in fluid mechanics, in a very brief manner, and I think that you have been exposed to thermal boundary layer concepts in heat transfer. But here I am going to have a more structured analysis of boundary layer concepts. What is called the boundary layer thickness, and how do we? There are different types of boundary layer thicknesses. The thickness that we normally associate with boundary layer is where the free stream velocity reaches 99%. I'm sorry, where the velocity inside the boundary layer reaches 99% of the free stream velocity. So what is a free stream velocity? What is an approach velocity? What is the velocity inside a boundary layer? And fundamentally, why should anyone bother to know and understand more about boundary layer? uh, is the transport process or the chemical engineering, what is the importance of boundary layer in chemical engineering? That is something which we would like to know. And you could also see that the aerodynamic boundary layer is also going to play a very important role in aerospace engineering, in mechanical engineering, in the design of ships and so on. So what happens inside a boundary layer? What kind of a flow? What is the friction coefficient? Uh, how do you solve boundary layer equations for flow over a flat plate, which is the simplest possible case and which I refer to here as the Blasius solution for flow over a flat plate. But in most of the realistic situations, when you are designing a car, when you are riding a bike, or when you are simply throwing a ball in the air, it's not going to be flow over a flat plate. So some other ways to treat or analyze boundary layer will become necessary. And that's where we come to this, the momentum integral equation. So instead of writing the differential balances, for example, a Navier-Stokes type of approach, we could go for an integral approach. So from a differential approach, how can we go to an integral approach? How would that be helpful? And one thing that we are almost certain of, that the boundary layers that we encounter are mostly going to be turbulent flow. So if it is turbulent flow, then obviously the Navier-Stokes equation in the form that you have studied in your second year will not be applicable. So what are the approximations for turbulent flow, especially turbulent boundary layers, one can introduce, which would give you some idea of fluid flow about immersed bodies? And there, of course, the most important thing is going to be drag. So how can I calculate the drag coefficient? How can I calculate the total force exerted by a moving fluid on an object of arbitrary shape? So this is going to play in an important role in our study of boundary layer concepts. So this is if you look at the first two topics, they are more or less similar to what you have done in fluid mechanics, but in the rest, the next two are completely going to be new. And in the Navisticks equation examples also, we will concentrate on something where we can apply the order of magnitude analysis for resolving the equation to a form which can be integrated. The next one is formulation and solution of heat transfer in laminar flow. So this you have done partly in your heat transfer classes. Now, you should tell me frankly whether or not you know about energy equation, whether this has been taught to you in the heat transfer part of the course. Do you recall anything from heat transfer? I'm not talking about Fourier's law. Some equation that relates the change in energy of a flowing fluid, and there could be conduction, which is obviously going to be dictated by Fourier's law. There could be convection, there could be heat generation due to viscous heat dissipation, and there could also be some amount of energy generation due to a reaction or due to a nuclear heat source or a resistive heat source. All those equations, all those energy terms taken together will give rise to energy equation. Are you aware of this or not? You have to respond. Otherwise, it gets very boring. I cannot see your faces. If you do not know, there's nothing wrong in it. Anyone, please tell me what it is. So, Shayan Maithri, I just see your name. Shayan, are you there? Or Polami? Sridipta? At least tell me that you are present in the class. I'm just asking you whether you have studied this or not. Sridipta, you are about to say something. There are about 65 students in the class. One of you please respond. What is wrong in responding, saying that we do not know or we do know? Anyway, so I do not assume anything about energy equation then. Um, the transient conduction, something which you probably have studied, where the temperature is of an object is going to change with time, apart from changing with space. So when can we use something simple analysis, which is known as the lumped capacitance model, where the temperature is assumed to be a function only of time but not of space. So what are the ways when can we make such an assumption that it's the temperature is function of time only? And of course you could visualize that if I give you a spherical object and it's at a high temperature and it is losing temperature to the ambient by convection at the boundary, then of course the temperature can be assumed to be a function of time only and not of space for different cases. For example, if the object is really small, then the resistance to conduction inside the solid object, which leads to a variation in temperature with space, can be neglected. So the length scale L of the object under consideration plays a role in assuming whether or not you can neglect temperature variation inside the solid. At the same time, if the thermal conductivity of the solid material, spherical solid material that I have provided to you, is very large, in that case, there may not be any variation in the temperature inside the solid, even though its boundaries are experiencing some sort of convective heat losses. So K, thermal conductivity, plays a role as well. And what is happening at the boundary is characterized by the heat transfer coefficient, the convective heat transfer coefficient. So this convective heat transfer coefficient depends on several factors. What's the condition at the outside and so on. So it's H, L, and K. H being the heat transfer coefficient, convective heat transfer coefficient, L being the length scale of the object which is under consideration, and K its thermal conductivity. Together, they provide us an idea of whether or not we can use the lumped capacitance model. Okay, so HL by K has a name. It's known as Biot number, and one should be careful in distinguishing the Biot number from the more common Nusselt number, which is also HL by K. But the difference between these two, HL by K that denotes Biot number and HL by K that denotes Nusselt number, can anyone tell me the difference? Am I audible?
In
At least
in Nusselt number, the K which we use is of fluid.
perfect. The Nusselt number, the K that we use is that of a fluid. And of course, since we are talking about the change in temperature inside the solid object, so obviously for the case of Biot number, the K is going to be that of the solid. So the differentiating factor between Nusselt number and Biot number is that the K in Nusselt number is that of the fluid, whereas the K in the Biot number is that of the solid. So that's the case. And we know that there are certain values of Biot number. I think it's less than 0.1 or something, in which case the lumped capacitance model is valid. And once a lumped capacitance model is valid, probably you'll also remember that it becomes a RC circuit. In the RC circuit, then you would get a relation instead of a PDE, you get an ODE of in time, and you would be able to solve for temperature. But there are situations in which the Biot number may not be less than 0.1. So what kind of solutions, analytical solutions, numerical solutions, some sort of graphical representation of results, which are also possible for which are also common for transient conduction. So we will see very quickly a part of that, but I will assume that it has already been covered by the heat transfer course. Then comes the mass transfer, and we know that mass transfer is slightly more complicated than the other processes. So we would try to see how do we develop the species balance equation. Okay, what is going to be the convective flow and natural convection both for mass and for heat. So we will take examples from heat and mass transfer. So with these backgrounds with us, where we know how to handle Navier-Stokes equation, energy equation, species balance equation, cancel the terms which are not important for a specific problem, arrive at the governing equation, identify the boundary conditions, integrate if possible, if it's an ODE, integrate to obtain the velocity profile, the temperature profile, or the concentration profile, we'd be able to obtain some idea of what is the drag coefficient, what is the overall heat transfer coefficient, or what is the overall mass transfer coefficient. But whatever I have discussed so far can only be done for simple systems. So if the system gets complicated, if the heat transfer is from a complicated geometry, a complex geometry, then this approach may not be possible, and you have to take the recourse of numerical solutions. But there are other ways of doing that. And the rest of the course will be devoted to identify the similarities between heat, mass, and momentum transfer. What are the similarity parameters which normally arise for such cases? For example, in most of the cases, the similarity parameters become apparent if you non-dimensionalize the governing equation. So if you think about momentum transfer, what can you name some at least one similarity parameter which you think would let you allow compare between systems which are having different velocities or different liquids, different conditions? Can you tell me what one
Reynolds.
similarity? Reynolds number, perfect. So Reynolds number is going to let me compare between situations where all these are going to be different. All these could be different. So everything is different, but the combination is such combination of velocity, density, viscosity, etc. are such that the Reynolds number is the same between two cases. Then we know that the flow pattern in these two systems are going to be similar. So that's why we call it as similarity parameter. It lets me compare between dissimilar, apparently dissimilar situations and arrive at some conclusions which would be equally applicable for both the cases. So there are other similarity parameters when you non-dimensionalize Navier-Stokes equation, which we could see, but the principal one being the Reynolds number. Similarly, when we try to analyze energy equation, which you may or may not know, what similarity parameter do you think would be relevant there in heat transfer? You have identified Reynolds number for the case of momentum transfer. So what such similarity parameter may arise? We will see how they arise, but which intuitively can you tell me what is going to be the similarity parameter in heat transfer?
Prandtl number.
Prandtl number. Absolutely right. Prandtl number is going to be the one in the case of heat transfer. So if it is Prandtl number in heat transfer, which number would be relevant in mass transfer?
Sherwood.
I'll
Schmidt number.
Sherwood and Schmidt. You may not remember what is Sherwood and what is Schmidt. Can anyone tell me which one is what? Sherwood is, I think, H suffix M, convective mass transfer coefficient, D, where D is the length scale, and divided by HMD by mu. That's what, no, not mu. HMD by DAB, where DAB is the where DAB is the uh, I think Prandtl number is Cp mu by K, where K is the thermal conductivity. Schmidt number is what is Schmidt number? Nusselt number is H L by K. Sherwood number is H suffix M. L is the length scale, and if this is K, then this has to be DAB. And this is a Schmidt number is mu by rho DAB or mu rho by DAB, one of the thing, which I probably it's like this, mu by rho DAB. Doesn't matter. We can always refer to the textbook and find out what is what. So do you see the similarity between Prandtl number and Schmidt number, Nusselt number and Sherwood number? So if I think about the heat transfer process, these are going to be my similarity parameters, and this obviously is going to be for my mass transfer process. Do you believe that Reynolds number should be there in heat transfer or and in mass transfer, or only Prandtl and Nusselt would be sufficient or would be the relevant similarity parameters? What do you think? Do I need to include Reynolds number as one of the possible similarity parameters in heat transfer or in mass transfer? You have identified, one of you have correctly identified Reynolds number to be relevant in fluid mechanics, momentum transfer. Would Reynolds number be also relevant in heat transfer?
Yes, sir.
Yes.
Yes, sir.
Can
Yes.
you tell me why? Your idea? You are absolutely right. Reynolds number should be present as a pertinent similarity parameter in heat as well as in mass transfer. Because Reynolds number essentially gives you some idea about the flow, the nature of the flow that is happening in a specific system. It's the interrelation between the viscous forces and the inertial forces which are present in the system. Some ratio of that is nothing but Reynolds number. So the moment we have inertial forces associated with Reynolds number, inertial forces means flow. So we also understand the flow plays a major role in any heat transfer process because of flow is associated with convective heat transfer. Similarly, flow is associated with convective mass transfer. So Reynolds number will always be associated as one of the similarity parameters in heat and in mass transfer as well. So that's why you would see everywhere that your Nusselt number relation or correlation is going to be some function of Reynolds number and some function of Prandtl number. On the other hand, say Sherwood number is going to be a different function of Reynolds number and Prandtl number. It could be Reynolds number to the power something or Prandtl number to the power something, but intuitively, even in the first class, we know that the similarity parameters are going to play a major role in identifying what's common in between these processes, what's common between heat and mass transfer process. Reynolds and Prandtl are some combination of these two must be
Sir,
there.
won't the Sherwood number be a function of Reynolds number and the Schmidt
I'm
number?
sorry. Yes, right. It should not be Prandtl number. It should be Schmidt number. So you could see that these combinations somehow will appear in any future study of the analogy between heat and mass transfer and also in momentum transfer. So the objective of this course is to find a logical way for the expression f1, f2 and the commonality between heat transfer coefficient and mass transfer coefficient. Because if we could do that, then what we could do, we could solve coupled heat, mass, and momentum transfer problems based on the analogy which we have just now described. So if we could solve for, let's say, the heat transfer part is solvable, but not the mass transfer part. But if we have the analogy, then the solution of the heat transfer part of the problem can be transposed to obtain corresponding mass transfer relations or correlations. Can we do that? Under what conditions we can do that? If the conditions are different, can we include some sort of a correction factor to still maintain the similarity between these two such that the relation of one can be interchangeably used as the relation for the second. And we know what is going to change when we make a transition from heat to mass. Somehow we have to replace Prandtl by the Schmidt number, and how would the relation change? How would this f1 and f2 change such that knowing this f1, I would be able to obtain f2 simply by replacing Prandtl number with Schmidt number. If we could do that, that would give me an operational advantage like never before, where the coupled problems can be solved by the practicing engineer in real life applications. So that's what this course is all about. Is there any question so far? Okay, so now we know the course, the textbooks, the grading strategy, the objective of the course, and let's concentrate then on the first two in the coming 2 or 3 classes. For solving for taking care of the first one, which will simply be a recap of the fluid mechanics which you have studied, I would expect that you remember some of it, not all of it, and I will quickly redo some of the problems which we have done before in fluid mechanics, and then go for more complicated applications, more complicated examples of use of Navier-Stokes equation before we move on to boundary layer. So I would expect that there would be one test based on the first part of it, the Navier-Stokes equation, the boundary layer concepts, momentum integral equation, and so on. So roughly this much is going to be the topic for the first test. Okay. Application of Navier-Stokes equation. I should be able to go quickly through this. You remember continuity equation. This is nothing but the conservation of mass, and in the differential form, the continuity equation takes on this form, which is for the Cartesian coordinate system, and you have also seen what's going to be the expression of this in cylindrical systems as well as in spherical systems. Then comes the equation of motion, or Navier-Stokes equation, where this is the vector tensor form of Navier-Stokes equation. The capital D obviously refers to the substantial derivative or the derivative following the motion, where if you expand it, it's simply going to be del V del time plus Vx del x plus Vy del Vx del y, and so on. So this is the substantial derivative, and if you come to this side, this is the pressure, this is the shear stress, and this is the body force. So in its present form, the way I have written it, Navier-Stokes equation is nothing but Newton's second law for an open system, where the fluid is allowed to enter and leave the system with a difference in pressure, could be a body force acting in the direction or in the opposite direction, that of the flow, which would be governed by the sign of this vector. So if we expand this equation in Cartesian coordinates, this is what you are going to get in the z component. This would be the form of this. So the first term would be the acceleration term, and the second, third, and fourth, where the velocity or velocity components appear explicitly, these three terms are collectively called as the convective transport of momentum. Because of flow, you have momentum transfer. So this is the transient term. These three are the convective term associated with it. This is the pressure gradient, which may apply in the direction of flow, assisting the flow or opposing the flow. These terms, and this is for a Newtonian fluid, so that's why I could write it in this specific form. And for a Newtonian fluid, the appearance of mu clear explicitly with these terms make them the viscous transport or molecular transport of momentum. So this is convective. These are convective transport of momentum. These are diffusive or molecular transport of momentum, where there is no net change in the molecular position, in the position of the molecules, but because of their vibration and because of the interaction through viscosity, the momentum gets transported from the faster moving layer to the slower moving layer and vice versa. Whereas this Gz is the Z component of the body force, and most likely body force that we most likely volumetric force that we likely encountered is gravity, though there could be electrostatic and magnetic and other forces as well. Depending on that, this shape is going to be different. One more thing which I did not discuss in detail for the case of fluid mechanics is that this is for a continuum system where the properties are going to remain same in all directions, and everywhere the number of molecules are such that continuum approximation is valid, which also means that the boundary conditions that are associated while solving this equation, and you probably remember the boundary conditions. One is going to be the no slip at the liquid solid interface and no shear at the liquid vapor interface. These are known to you. So these type of boundary conditions are only valid for continuum situations, but this equation, the Navier-Stokes equation, cannot be written for a system which is very dilute, okay, which is a rarefied gas. Flow in a rarefied gas, if you write the Navier-Stokes equation, that's not going to be correct. There you have to modify the boundary condition, and the how close a system is to equilibrium to continuum is denoted by a number which is known as the Knudsen number. So lesser the value, smaller the value of Knudsen number, the closer it is going to be near continuum. So at one end of the spectrum, you have very low value of Knudsen number, and that is a continuum system for which Navier-Stokes equation, no slip condition, no shear conditions are valid. Most of the systems that we encounter in engineering applications are in continuum. But there are other systems in engineering applications as well where this continuum may not be maintained. For example, flow of rarefied gases, for which, depending on the value of Knudsen number, we may have to modify the boundary condition by incorporating a slip at the interface, liquid solid interface. The velocity is not going to be zero, the relative velocity is not going to be zero at the liquid solid interface, but it could have a finite velocity which is known as the slip velocity. And at the other end of the spectrum, where the Knudsen number is about 10 or more, the Navier-Stokes equation, the continuum approach fails completely, and one has to use either a Monte Carlo approach, kinetic Monte Carlo approach, or in the farthest from the continuum approach, one has to use the kinetic theory approach. But we will not consider about the slip, the molecule, the Monte Carlo simulation, or this free molecular flow. In our present situation, we will restrict ourselves when no slip boundary condition is still valid. A problem which we have done before. I'll quickly go through this. So you have a disk storage system. Do you recall this problem? I think I have solved it in fluid mechanics.
Yes, sir.
Okay, so it's nothing but a disk which is being rotated at high speed, 3600 RPM, and you have a head which is 10 millimeter by 10 millimeter, and it doesn't touch the disk. It floats on the disk with an airflow in between, which is air gap in between, which is very small, 0.5 micron, and the viscosity, density, etc. provided. You need to find out what's the Reynolds number, the viscous shear, and the power required to overcome the viscous shear. The key feature of this kind of problem is that for such a small gap, which is 0.5 micron, the flow is nothing but flow between parallel plates, which is something which we have done before. So one is obviously the Quaith flow. You probably recall the Quaith flow. One plate is stationary, the other plate is moving with a liquid in between. So obviously the motion of the top plate is going to impart velocities in the layers, adjoining layers below, and due to viscosity, the layers are going to start moving progressively with lesser velocity towards the right, as you see. and without in absence of any applied pressure gradient. So the flow initiated by the motion of the top plate in absence of pressure gradient is known as the Kweith flow. So if you recall this problem, it is nothing but a Kweith flow problem because there was no applied pressure gradient, and it's only one of the surface is moving at high speed, the other one is stationary, and since the gap is too small, the radius is too large as compared to the size of it, then it can be treated as flow between parallel plates. The other one that for this case is that pressure gradient driven flow. This have we have also have seen when both the plates are stationary, you just apply a pressure and you are going to get some sort of a parabolic distribution with the highest velocity, with the maximum velocity being at the center line. And of course, the pressure has to progressively decrease in the direction of flow in order to make it a favorable pressure gradient. So the precondition for flow towards the right of the figure that I have drawn is that del P del X must be less than 0. When you combine these two, Kweith flow and pressure gradient driven flow, what you get is some sort of a profile like this, where the top plate is moving, the pressure gradient is also there. So the velocity here due to no slip condition must be equal to capital U, whereas the velocity may be more than capital U or less than capital U. The figure it shows is that the velocity, maximum velocity, is more than capital U, and that can happen when the applied pressure gradient is going to be large in compared to the Kweith flow driven velocity, and you get a bulging out of the velocity profile. Okay. If it is not, if the pressure gradient is quite small, then it's not going to be linear. There's going to be some departure from the linearity of the profile, but the maximum will still be at the top plate. You recall our discussion on this in a previous classes. So if it could probably be something like this. Okay, so some pressure gradient is being applied, but not much, such that the maximum is still going to be over here. And the other one, if you remember, let's say that the top plate is moving, but instead of del P del X less than 0, I have del P del X greater than 0. So the profile could be something like this, which is the case for dP dx greater than 0. So the velocity will still be equal to u, but the positive gradient will force some of the liquid to move towards the left, some of the liquid will move towards the right because of viscous drag exerted by the top plate, and this is because of the pressure driven flow to the left of the figure that I have drawn. And I think you have solved problems in which there could be no flow such that the area under these two curves would be the same. So you could tune the dpdx in such a way that there may not be any flow, any net flow in any of the direction. So you have done that kind of problem before. So this is something which is quite common, well discussed in fluid mechanics class. Do you have any question? Okay, so I'll skip this solution part, which since I'm going to upload it anyway, so you could find out what how to calculate that, but it's pretty straightforward. You know what's the velocity, you can calculate what's the Reynolds number, and you can find out what is the shear stress, you can find out what is the force, and once you know the force, you can find out what's the torque, and once you have the torque, you can calculate what is the power dissipation rate. So I'll leave this. You can take a look at it later on. This problem I think I have also solved in fluid mechanics. This is just the recap of what we have done. So we have an oil spill and a boat which moves on the river, and there is an inclined part to it, and the pulley simply moves like this. As it moves like this, the oil the yellowish part in the figure, the oil gets dragged by the moving, moving, what would I call the belt. It's being dragged all the way and it's released to a tank. So that way, with the movement of the boat, the oil from the top of the river can be brought to the tank. So we need to find out what is the discharge of the oil into the tank and the force acting on the belt and the power required. So fundamentally, it's exactly the same as the almost exactly the same as the previous problem. So what you need to do is you need to write the x component of the equation of motion. So this is the x direction, and you could obviously cancel out the terms which are not relevant here. Of course, this is steady state, so u is not a function of u is not going to be a function of time. What about the second term? U del x. Should we have this term?
No,
Can you specify why?
because u will vary in the direction of y.
Perfect. And what is that called if u varies only in the direction of y but not in x? There is a specific name to it. You are absolutely right, but could you tell me what kind of a profile is that called?
Laminar.
Not laminar. Say in this region where at the entry point you you may not be a function of y alone. It could be a function of x, but beyond some x, after it traverses some distance, it's going to be only a function of u, not a function of x. So that has a special name to it. Do you recall that?
Sir, is it creeping flow?
No, creeping flow is a very slow flow in which the viscous forces predominate over the convective flows. So that it is not creeping flow. This is known as the fully developed flow. So the fully developed flow is the one in which the velocity varies with one direction but doesn't vary in the direction of flow. So u is not a function of x. U could be a function of y, as one of you have pointed out, but u is definitely not a function of x. So that's called a fully developed flow. So u may be non-zero, but u is not a function of x since it's fully developed flow. And I have identified that at the beginning, at the entry point, near the entry point, this condition may not be satisfied. The third term
0.
and reason,
There is no V.
there is no v, there is no w, so both these terms are going to be zero. There is no imposed pressure in the system. Okay, so it simply drags the fluid, it doesn't apply any pressure. Of the three terms inside the third bracket, which one is going to remain?
d2u by dy square.
Yes, the rest fully developed, and u is not a function of z. So these two will go away, and of course this the rho gx, the right component of g would be present. So therefore your governing equation simply becomes the third term on the right hand side and the last term on the right hand side. These two are going to be the non-zero terms and they will constitute the governing equation. So this is what is your going to be your governing equation. And of course the boundary conditions are the no slip conditions, that at y equals 0, that means right at the bottom the velocity is going to be 0, whereas at y equals delta or whatever be the thickness at y equals h, the velocity is simply going to be the constant velocity of the belt. So with these two conditions, you should be able to solve for this velocity, and this is what the velocity is going to look like. So it's a function of the inclination angle and it's a function of u as well. Now, if you see that in this case, if you get rid of the body force, which is denoted by rho g sine theta term, what you get is a linear distribution of velocity, only the last term, which is typical of Couette flow. So if this problem is, if this is horizontal, then the gravity will not have, body force will not have an effect, but still liquid is going to be pulled in this direction, in the direction of the motion. So there the flow is simply going to be Couette flow, and it is simply going to be the last term. So one now can find out what is the volumetric flow rate. And the volumetric flow rate also, you would see that one term is due to Couette flow, the other term is due to the body force. And of course, the body force acts in the direction opposite to that of the flow. It reduces the flow, that's why it comes with a negative. Whereas this drags the liquid up, so because of Couette flow, so that's why it comes out to be positive. So one could find out what, by plugging in the number, what is the flow rate. You can find out what is the shear stress, since you have the velocity distribution. So you should be able to find out what is the shear stress, and the shear stress multiplied by the area gives you the force. Force multiplied by the velocity would give you what's the power necessary in order to suck the oil out of the river into the boat. Any questions so far? So these are a quick recap of our fluid mechanics class. I'd spend maybe one more class on the problems that we have solved before, then moving on to more involved problems, as I have said, that may involve, may or may not may involve order of magnitude analysis to reduce to simplify the governing equation. So if there are no more questions, I once again thank you. I would urge you to remain safe, and we'll meet again on Friday.